Right now, as you sit here, a 7 billion-year-old wanderer is racing toward the sun. Its icy skin has been hardened by epochs beyond imagination, its path traced across a galactic backdrop older than life on Earth. Yet the mystery that keeps astronomers awake at night isn't what it is. It's why it has chosen to arrive in this particular moment, in our lifetimes, when we finally have the eyes to notice. On the first day of July 2025, survey telescopes scanning the heavens picked up a faint moving point of light. At first, it looked like any one of the countless comets that drift into the outer solar system every year. Yet within hours, orbital calculations revealed something extraordinary. Its trajectory was hyperbolic, meaning it was not bound to the sun. This object, later designated 3I Atlas, was not born here. It was a traveler from deep space, 420 million miles from the Sun at the moment of discovery, streaking inward on a once-in-an-eternity pass. The scientific community reacted with a strange mixture of exhilaration and disbelief. The exhilaration was obvious. Another confirmed interstellar visitor, the third in human history. The disbelief came from the timeline. For thousands of years of recorded human observation, there had been nothing. No confirmed comets or asteroids from other stars. Then suddenly, within just 8 years, 3 of them had crossed our skies. First came the needle-shaped One-Eye Oumuamua in 2017, mysterious in its form and behavior. Next was the unmistakably cometary 2I Borisov in 2019, leaving behind a luminous tale of alien chemistry. Now, in 2025, here was 3I Atlas, joining the procession as if the universe had suddenly opened a secret gate. To grasp the improbability of this sequence, imagine watching a vast desert plain for your entire lifetime, expecting nothing but wind and silence. Then, within a single afternoon, 3 strangers appear from 3 different horizons, each carrying their own stories, each arriving almost simultaneously at your doorstep. Such is the strangeness of what astronomy is experiencing right now. The question is not whether these objects exist. Billions, perhaps trillions of them must wander the galaxy. The question is why the first arrivals chose this particular decade, this sliver of time within the immense tapestry of cosmic history. Consider the scales involved. 3I Atlas has been traveling through interstellar space for more than 7 billion years. That is longer than the age of our sun, longer even than the Earth itself has existed. For most of its journey, it drifted unnoticed, frozen in the blackness between stars, nudged by the faintest of gravitational pulls. The chance that such a traveler would just so happen to pass near our world precisely now, precisely when we have developed instruments capable of spotting it, seems almost absurd. Astronomers are trained to distrust coincidence, yet the sequence of recent discoveries feels like one. Before 2017, interstellar visitors were the stuff of speculation, whispered about in papers but never confirmed. Then, suddenly, 3 in under a decade. The sheer unlikelihood creates a tension that gnaws at both scientists and philosophers alike. Is this only the result of new technology, the simple consequence of better eyes scanning the skies? Or is there something deeper at work, some cosmic rhythm that has aligned the trajectories of ancient wanderers with the present moment? Picture it this way. Imagine standing in a remote village, far from any road, expecting no travelers. For centuries, no one passes by. Then, within a single day, 3 strangers from 3 different continents knock on your door, each unaware of the others, each arriving by chance. Do you believe in coincidence, or do you begin to suspect that the road you thought was abandoned is, in fact, part of a hidden route you had never noticed? This is the predicament of modern astronomy in the wake of 3I Atlas's discovery. Scientists can calculate orbits and velocities with precision, but the timing of these encounters is harder to quantify. It feels as if the cosmos has chosen this moment to reveal itself. When the telescopes locked onto 3i Atlas, its presence was almost ghost-like, a faint spark against the starry field, dim and yet insistent. Astronomers immediately began working out its path. They discovered that by October 30th, 2025, it would sweep past the Sun at a distance of 1.4 astronomical units, just beyond Earth's orbit. By December, it would make its closest approach to Earth, still 167 million miles away, but close enough for weeks of intense observation. Then, just as quickly as it had come, it would vanish back into the dark, never to return. The details of its trajectory are not what trouble scientists most. Those can be calculated. What troubles them is the sense of improbability, the feeling that the universe has arranged a series of appointments for us, as though placing messages in bottles and letting them wash ashore only when someone is there to pick them up. 3 visitors, 3 entirely different origins, 3 entirely different forms, yet all arriving in the same span of years. One might dismiss it as simple luck, the result of better telescopes and more sensitive surveys. After all, our instruments have improved dramatically in the past decade. Automated systems now scan the entire visible sky every night, something unimaginable a century ago. The moment we had the eyes, perhaps the cosmos was bound to show us what had been there all along. But even with this explanation, the timing remains haunting. If these objects have been drifting for billions of years, why did our era become the first to see them? Why not 500 years earlier, when Galileo first raised his crude telescope to the heavens? Why not 500 years later, when humanity might be traversing the stars ourselves? Why now, in the narrow window where we are curious enough to notice, yet still grounded enough to wonder? This question has already sparked heated debates in astronomical circles. Some argue that it is nothing more than statistics catching up with reality. Interstellar visitors must be common, and once we achieve the technology to detect them, they would appear. Others point to the remarkable clustering of events in such a short time frame, suggesting that the solar system may currently be moving through a denser region of galactic space, a sort of cosmic thoroughfare where wandering debris is more abundant. But underneath these scientific discussions lies a quieter, more unsettling thought, that perhaps the timing itself is part of the story. Perhaps the universe has rhythms and cycles we are only beginning to glimpse, and we happen to be standing at a point of convergence where ancient paths cross our own. As 3i Atlas glides closer, every calculation, every telescope image, every new fragment of data only deepens the question. Its very presence is an echo of journeys begun before our world cooled from molten rock, before our sun lit up the sky. It is the embodiment of deep time made visible, crashing into our present moment with a force not of destruction, but of meaning. To call it coincidence feels insufficient. To call it destiny feels premature. Yet the feeling persists that this is not just a chance encounter, but part of something larger, a rhythm we do not yet understand. The desert plain is no longer empty. The strangers have begun to arrive. The door has opened, and the silence of eons has given way to a sudden chorus of footsteps. The question that haunts astronomers is whether these footsteps are random echoes or the first notes of a pattern playing itself across the galaxy. The desert plain is no longer empty. Strangers have appeared, each carrying its own history, each converging upon us as though summoned by a pattern we cannot yet read. But the language of science demands more than metaphor. It demands numbers. It demands probabilities. It demands a reckoning with mathematics that, in this case, refuses to sit quietly in its equations. For almost all of human history, the tally of confirmed interstellar visitors was 0. Not a single one had ever been seen passing through our skies. We catalogued tens of thousands of comets and millions of asteroids, all of them local to our solar system, and still the number of alien wanderers remained fixed at nothing. Astronomers could construct theories about their existence, run simulations of how stars might eject icy debris during planet formation, but no one had proof. The ledger was blank. Then the silence broke. In 2017, the mysterious shard we named One Eye appeared, its path so steep and its velocity so high that only one explanation fit: it came from the stars beyond. 2 years later, a second, unmistakably cometary traveller swept through. By 2025, yet another joined their ranks. 3 interstellar objects in only 8 years, 3 where there had been none before. It was as if the cosmic dice, rolled endlessly for billions of years, suddenly came up triple sixes in rapid succession. The odds, at least on first glance, should not allow such a thing. Astronomers had long expected interstellar debris to pass through, but they also believed the chances of catching one in action were vanishingly small. Our solar system is tiny compared to the galaxy around it. To imagine detecting 3 visitors in less than a decade is like tossing a coin into the ocean and watching it land at your feet 3 separate times. The statistical nightmare begins when you try to reconcile expectation with reality. Before 2017, estimates for how often we might detect an interstellar visitor ranged from once every few decades to once every few centuries. The number depended on assumptions about how many objects drift between the stars, how wide our survey nets stretched, and how reflective those objects might be. The gulf between theory and observation is what unsettles astronomers. The universe has handed us not 1 or 2 anomalies, but a streak of them, forcing us to question our math, our methods, or perhaps our assumptions about the very structure of galactic space. To understand the scale, consider our own backyard, the Oort cloud. This hypothetical halo of icy bodies, extending trillions of miles from the Sun, is thought to contain billions, maybe trillions of objects. From time to time, gravitational nudges send one tumbling inward, giving us the comets we see streaking across the sky. If our solar system ejects material outward during its lifetime, so must every other star. Multiply by the hundreds of billions of stars in the Milky Way, and suddenly you can imagine a galaxy rich with orphaned comets and asteroids, each one a relic of some ancient planetary system. Yet abundance does not equal visibility. Space is vast beyond comprehension. Even if trillions of interstellar objects drift through the galaxy, they are scattered through volumes so large that any single object is like a grain of sand drifting in an ocean larger than all the Earth's seas combined. That is why, for so long, astronomers assumed we would rarely see them. The darkness is not empty, but it hides its treasures too well. This makes the appearance of 3 in quick succession so puzzling. Why were these particular objects bright enough, close enough, trackable enough for us to notice? Out of countless billions, why them? Why now? The statistical puzzle is not merely that they exist, but that their paths intersected with the tiny cone of human perception in this brief window of time. Part of the answer lies in technology. For centuries, comets were spotted by chance, visible only when they became bright enough for the naked eye. Even through the 20th century, many were still discovered by amateur skywatchers with small telescopes. But in recent decades, the rise of automated surveys changed everything. Projects like the Catalina Sky Survey, the Pan-STARRS telescopes in Hawaii, and the Atlas Network began sweeping the skies with relentless precision. Night after night, they scanned every corner of the heavens, comparing images in real time to catch faint points of light in motion. Computers joined the hunt, combing through oceans of data faster than any human observer could. Suddenly, the invisible became visible. This shift marks a threshold. Before 2017, interstellar visitors may have passed by unnoticed. They could have drifted within millions of miles of Earth, glowing faintly, too dim to trigger our instruments, too fast to distinguish from the background stars. Once our surveys reached a certain sensitivity, however, the cosmic gate seemed to open. Objects that would have slipped by undetected were now caught in our nets. In that sense, the cluster of discoveries may not represent a sudden influx, but rather a sudden awakening of our perception. Yet even this explanation does not fully quiet the unease. Think of it in terms of probability. Imagine a lottery so difficult that experts predict only one winner per century. Now imagine not one, not two, but three winning tickets drawn in less than a decade. It is possible, certainly. Statistics allow for outliers. But when improbabilities stack upon improbabilities, the human mind resists simple explanations. We begin to suspect that the game itself has rules we have not yet discovered. The metaphor of the lottery resonates because it highlights both chance and inevitability. If enough tickets are sold, someone must eventually win. If enough interstellar objects exist, some must eventually pass close enough to be seen. But to win 3 times in rapid succession feels like the universe is pressing its luck, nudging us to notice, daring us to ask harder questions. Astronomers are now reworking their models in light of these detections. Estimates for the density of interstellar objects have risen dramatically. What once seemed rare now appears common, perhaps overwhelmingly so. Some studies suggest that for every star in the galaxy, there may be thousands of wandering objects drifting freely. If true, our solar system might constantly be brushing past them, like swimmers in a crowded sea who never realize how many others are moving beneath the surface. The discomfort arises not only from the numbers, but from the patterns. 3 in 8 years is not just statistically unusual, it is narratively suggestive. Our minds are wired to seek patterns, to connect dots, to wonder if coincidence hides design. The mathematics forces us to walk a thin line between skepticism and awe. Perhaps this is all selection bias, the result of better eyes and better algorithms. Or perhaps we are standing at a crossroads in the galaxy, a place where the traffic of stars and their cast-off debris happens to converge. Each new detection brings more data, but also more questions. What shapes their paths? Why do they arrive clustered in time? How many have slipped past us in centuries before our instruments became sharp enough to catch them? The numbers refuse to sit still. They shift with every new observation, mocking our attempts to pin them down. The unsettling part is not that we lack answers, but that the questions keep multiplying. Mathematics is supposed to clarify, to make sense of chaos. Yet here, the equations draw us into deeper mysteries. They whisper that our galaxy may be more crowded than we ever believed, that the darkness between stars may be alive with unseen travelers, that the odds we once trusted are not the odds at all. The desert plain, once thought silent, may in fact be bustling. We simply lacked the ears to hear, the eyes to see. Now that our instruments have sharpened, the chorus has begun. The probabilities bend toward presence. The equations strain to encompass reality, and the numbers that once said impossible now say inevitable. Still, inevitability does not explain why the encounters feel so sudden, so concentrated, so eerily timed with our own awakening. To wrestle with that question, we must step beyond numbers into the grander stage of galactic motion, into the cycles of stars and the currents of the Milky Way, where timing may not be coincidence at all, but the unfolding of deeper rhythms yet unseen. The equations strain to encompass reality, yet even numbers falter without the context of motion. Our solar system is not suspended in stillness. It is bound to an immense orbit, circling the center of the Milky Way in a cycle that takes about 230 million years. One galactic year outlasts the span of entire geological ages on Earth. To measure time this way is to realize that the extinction of the dinosaurs, the rise of mammals, and the emergence of human beings have all taken place within a single fraction of one orbit. Right now, we are somewhere along that track, carried forward by the sun's gravity well, with every planet, asteroid, and comet held fast in its embrace. Where we are in this vast rotation matters. Just as a car driving through different neighborhoods will pass through streets that are empty and others bustling with pedestrians, our solar system moves through regions of the galaxy that differ in density, composition and activity. Some stretches are sparse, quiet lanes where few stars reside. Others are crowded intersections filled with ancient debris, streams of material stirred long ago by gravitational tides. The neighborhood we pass through can shape the kinds of cosmic encounters we experience. Astronomers believe 3I Atlas may trace its origin not to the thin disk of the galaxy where young stars like our Sun dwell, but to the thick disk, a structure layered above and below the familiar plane of spiral arms. The thick disk is home to stars far older than our own, stars that were born in the galaxy's youth and still carry the scars of early turbulence. Their orbits tilt at steeper angles, their paths less ordered, their histories written by collisions and mergers that shaped the Milky Way billions of years ago. The material they shed, asteroids, comets, planetary fragments, moves with different dynamics than the debris of younger systems. To encounter an object from this population is to intercept a messenger from a more ancient epoch, bearing chemistry and structure forged in a galactic environment very different from our own. The current region of the galaxy through which we are traveling adds another layer to this puzzle. Stellar density is not uniform across the Milky Way. Gravitational influences vary depending on whether we are skirting the edge of a spiral arm, passing near an open cluster, or drifting through an inter-arm void. Each setting produces its own cosmic weather, zones where stars pull more strongly on passing bodies, regions where debris fields are stirred and scattered, corridors where interstellar travelers are more likely to be nudged onto paths that cross our own. The sudden appearance of multiple interstellar visitors within a short span of human years may not be random coincidence at all. It may reflect the fact that we are currently passing through a galactic neighborhood where such encounters are simply more common, as though we have driven our car into a district where the sidewalks are crowded and crossings frequent. This perspective reframes the timing of 3I Atlas. Its presence may be less a matter of improbable luck than the natural result of location. Our solar system, endlessly orbiting, may have entered a traffic pattern, an interstellar flow of ancient debris aligned with the thick disk's stellar motions. In such a region, wandering objects might not be rare at all. They might drift past in steady procession, unseen by earlier generations only because our eyes were too dim to catch them. Now, with telescopes sensitive enough to sweep the sky nightly, we find ourselves recognizing the pedestrians who have been walking here all along. Spiral arm dynamics add yet another rhythm to this journey. The galaxy's arms are not fixed structures, but waves of higher density, like traffic jams that persist, even as individual cars move in and out of them. As our solar system drifts through these arms, it experiences changes in gravitational influence and star formation activity. New stars ignite, clusters scatter, supernovae explode, and debris streams shift. Each passage through a spiral arm could increase the likelihood of close encounters with interstellar matter, just as entering a crowded boulevard increases the chance of meeting travelers compared to the empty outskirts. Where we are in relation to these arms shapes what we see, and perhaps explains why this decade has become a decade of arrivals. In this light, the appearance of 3I Atlas is not an isolated fluke, but part of a broader choreography. The thick disk origin hints at ancient populations feeding objects into our path. The density of our current neighborhood may funnel them closer than before. The spiral arm cycles create periodic windows where such encounters become statistically richer. When combined, these influences suggest that our galactic position at this moment is far from arbitrary. It is as though the solar system, in its long orbit, has steered itself into a crossroads where multiple streams of cosmic travelers intersect. The imagery of a car passing from one neighborhood to another captures this elegantly. On one block, the sidewalks are bare, the air still. On the next, people crowd the crossings, bicycles weave between lanes, and the flow of life surges around you. The driver has not changed. The vehicle is the same, yet the experience of motion transforms entirely depending on where the road leads. So it is with us, passengers on a star moving through the Milky Way's neighborhoods, suddenly aware that the density of pedestrians has increased and that the likelihood of meeting strangers has multiplied. If this interpretation is true, then the mathematics of coincidence shifts again. 3 visitors in 8 years may not be improbable at all, but a natural reflection of our current position in the galaxy. The real mystery becomes not whether such encounters should happen, but what greater cycles and patterns govern their timing. To probe this further, one must look not only at our galactic orbit, but also at the awakening of our technology, the widening of our cosmic eyes at the exact moment when the sidewalks grew crowded enough to demand our attention. The sidewalks may have been crowded for ages, but until recently we walked half blind, unable to recognize the passers-by who brushed close to our world. For most of human history, interstellar visitors could have streamed silently through the solar system without leaving the faintest mark on our records. Telescopes swept narrow slices of the heavens, astronomers peered through eyepieces, and vast populations of objects slipped by, lost to the night. The limitation was not absence, but perception. We did not yet have the eyes to see. That changed with the rise of automated sky surveys. The Asteroid Terrestrial Impact Last Alert System, ATLAS, now scans the entire visible sky every 24 hours, a feat unthinkable a generation ago. Twin observatories in Hawaii, joined by newer installations in Chile and South Africa, sweep methodically across the dome of night. Their cameras, built from high-efficiency CCD detectors, gather torrents of data, while computer algorithms parse it in real time, searching for faint points of light that move against the fixed background of stars. Each night is a census of motion, repeated again the next night, until patterns emerge and trajectories are drawn. This capability marks a threshold, a crucial moment in the story of perception. Before 2017, the technology to spot small, fast-moving objects from beyond the solar system simply did not exist at scale. Interstellar bodies may have entered and departed countless times, but they were too dim, too swift, and too unfamiliar to trigger recognition. They blended with the millions of asteroids bound to the sun, slipping through unnoticed like shadows on the periphery of vision. Humanity was effectively nearsighted, gazing upward without the glasses required to resolve what was truly there. The breakthrough came with a combination of sensitive detectors, rapid computing, and automation. CCD cameras transformed astronomy by replacing the human eye with silicon precision. Another anonymous traveler, uncounted and unseen. Its detection was not merely a stroke of luck, but the culmination of decades of progress, the moment when our eyesight sharpened just enough to glimpse what had always been there. From that point onward, a network effect transformed the process of discovery. Once an anomaly was flagged, telescopes across the world could pivot within hours to track it, each adding observations that refined the orbit, confirmed the interstellar nature, and captured details before the object slipped back into darkness. This coordination, enabled by instant global communication and shared data protocols, allowed humanity to respond as a unified organism, our collective gaze converging on a single cosmic intruder. The speed of response mattered because such objects move fast, visible only for brief windows before fading into the black. Without rapid confirmation, they would vanish into uncertainty. The synergy between advancing hardware and computational power made this coordination possible. Moore's law, the exponential growth of processing capability, finally caught up to the scale of astronomical need. The challenge of tracking countless points of light across the sky every night is a problem of pattern recognition, a task machines excel at only when they can crunch terabytes of data swiftly enough to distinguish a genuine interloper from noise. For the first time in history, our tools matched the scale of the cosmos's subtle signals. What had once been overwhelming became manageable, even routine. To grasp the transformation, imagine walking nearsighted through a city for millennia, shapes blurring together, details dissolving into haze. You know the world is populated, but you cannot discern the faces that pass you, nor the intentions carried in their steps. Then one day, you put on glasses for the first time. The outlines sharpen, crowds resolve into individuals. Every passerby is no longer a blur, but a presence, unique and undeniable. This is what astronomy has undergone in the past decade. Not a change in the universe, but a change in our clarity, the sudden revelation that the pedestrians were there all along. The awakening of our cosmic eyes redefines coincidence. 3 interstellar objects in 8 years may feel improbable, yet in truth, the improbability may lie in the blindness that preceded it. How many others swept through unnoticed before the cameras were vigilant, before the algorithms learned to recognize? The mystery may not be that they are appearing now, but that we only just learned how to see them. The sidewalk is no more crowded than before, but the world has finally come into focus. What follows from this shift is a profound reorientation in how we perceive our place in the galaxy. If interstellar visitors are not rare flukes but constant presences, then every detection is not an isolated marvel but part of an ongoing dialogue, one we are only now learning to hear. The glasses are on, the crowd has resolved into clarity, and the realization dawns that the city has always been full of strangers passing close enough to touch. The revelation of vision sharpened is only the beginning, because once an object is detected, its path becomes the next mystery. A speck of light on a digital frame is quickly transformed into numbers, those numbers into equations, and from those equations emerges a trajectory, a signature written in motion. For 3I Atlas, that trajectory is not circular like the planets, nor elliptical like comets that return, but hyperbolic. Its path curves around the sun once and then departs forever, a mathematical fingerprint proving it does not belong to this system. No gravitational tether binds it, no orbit calls it back. The numbers themselves tell the story. On October 30th, 2025, 3I Atlas will reach its closest approach to the Sun, its perihelion, at a distance of 1.4 astronomical units. This is just a little farther than Earth's distance from the Sun, a range that places it squarely within our reach for sustained observation. Weeks later, on December 19th, it will pass closest to Earth itself at 167 million miles, near enough for telescopes around the globe to study it in detail. This is not a fleeting glimpse like a meteor streaking across the sky, but an extended encounter, a window of months where science can take its measure. Such precision is no accident. Interstellar objects travel at speeds that dwarf most solar system comets, often tens of kilometers per second relative to the Sun. That velocity makes them difficult targets, too faint if distant, too quick if near. Yet 3I Atlas follows a geometry that seems almost tailored to human attention. Its angle of approach, its velocity relative to Earth, and the timing of its perihelion all combine to maximize visibility, offering a choreography so precise it feels rehearsed. One could imagine a dancer stepping into a spotlight at just the right moment, pirouetting gracefully through the stage and vanishing into the wings, never to return. At the heart of this elegance lies the mathematics of hyperbolic motion. Bound orbits, circles, ellipses are the familiar rhythms of solar system mechanics. But when an object comes from beyond, its energy exceeds the gravitational grip of the Sun. The curve it follows is an open arc, a hyperbola described by equations that guarantee escape. No matter how near it passes, the Sun cannot capture it without a perfect chain of improbable interactions. The object is destined to leave, carrying with it the imprint of its brief passage. This is the unmistakable signature of interstellar origin, not just speed, not just angle, but the certainty of departure. The sun itself plays a vital role in shaping the spectacle. As 3I Atlas dives inward, solar gravity bends its course, not enough to bind it, but enough to create a deflection, a swing that brings it closer to Earth's vantage. This gravitational assist is the same principle used to slingshot spacecraft through the solar system, leveraging the pull of massive bodies to redirect momentum. In the case of 3I Atlas, the sun acts as a choreographer, drawing the visitor into a sweeping curve that ensures both visibility and departure. Without that gravitational shaping, its trajectory might have carried it too far, too faint, beyond the reach of our instruments. The escape velocity at perihelion underscores the finality of the encounter. At 1.4 AU, the sun's gravity still tugs with immense force, but the object's speed ensures freedom. It races past at more than the 42 kilometers per second required to leave forever. There is no slowing, no hesitation, only a brief surrender to curvature before straightening again into the infinity of interstellar space. For all our telescopes and instruments, this is a one-time performance, unrepeated, unrepeatable. We are given a single chance to observe before it slips into the dark beyond recall. The timing of this passage is especially striking. October 30th offers optimal geometry, the sun low enough in the sky relative to Earth's position that nights are long, observatories spread across both hemispheres can track it, and months of visibility follow before it fades into the distance. December's Earth approach extends the opportunity, offering a phase when the object is bright enough for spectroscopy, for radar attempts, perhaps even for space mission proposals if imagination proves bold enough. This is the cosmic equivalent of a guest arriving not just unannounced, but at the exact hour when the lights are on, the observers awake, and the instruments ready. The analogy of a dance remains apt. Imagine a performance in which every entrance is timed to the beat, every gesture aligned with music unheard but felt. The sun is the conductor, gravity the rhythm, Earth the audience seated perfectly to see the display. 3I Atlas enters stage left, curves through the spotlight, bows near the orchestra, and exits stage right. The precision is breathtaking. To miss the performance would be to miss it forever, for there is no encore, no return engagement. Such timing invites questions that extend beyond mere mechanics. Why should the geometry align so well with human capability? Why now, in the narrow window of decades when our technology is adequate to track, measure, and record? The orbital elements can be explained by mathematics, but the coincidence of circumstance lingers. We are left with the sense of a door briefly opening in a corridor of locked rooms, a chance alignment that may not recur in 1,000 years, yet arrives precisely when our eyes are clear. The dance of 3I Atlas also reminds us of the fragility of opportunity. Had its perihelion been half an astronomical unit closer, solar glare would have blinded our view. Had its Earth approach been weeks earlier or later, our planet would have been poorly placed, its visibility cut short by daylight or seasonal interference. Shift the timing by a small degree, and the choreography collapses. But as if by design, the steps fall exactly into place, granting us not just detection, but study, not just knowledge of its existence, but a chance to interrogate its nature. Each calculation reaffirms the uniqueness of the event. Astronomers model the trajectory, plot the hyperbola, project the exit vector. They know where it will be, when it will fade, how fast it will recede. Yet in those cold predictions lies a strange warmth, the recognition of a fleeting intimacy. For months, 3I Atlas will be ours to follow, ours to measure, ours to learn from. Then it will be gone, carrying our questions unanswered into the dark. The perfection of this orbital timing leads naturally into a larger consideration. Is such choreography merely chance, or does it reflect patterns on scales grander than we can yet grasp? To answer, we must widen our view once again, looking beyond mechanics to the larger galactic cycles that shape the stage upon which such dances unfold. The elegance of a single orbit cannot be separated from the greater stage upon which it plays. For every hyperbolic arc that carries a visitor through our skies, there are deeper cycles in motion, cycles not measured in months or years, but in millions and billions. The arrival of 3I Atlas cannot be understood solely through the pull of the Sun or the timing of Earth's alignment. It must be seen against the backdrop of the Milky Way itself, a system alive with rhythms older than the planets, older than the Sun, older than the very dust that composes this object. Our solar system is not fixed in place, but drifts within the galaxy, orbiting the central bulge over the course of roughly 230 million years. Each galactic year carries us through spiral arms, across star-rich neighborhoods, through voids where stellar populations thin. Along this journey, the gravitational environment shifts constantly. Streams of material left behind by ancient stars, disrupted clusters, and the slow currents of galactic rotation sweep across our path. Some regions are quiet, like empty intersections at midnight. Others are crowded, full of debris and wandering bodies, like a market street at noon. At present, the evidence suggests we are passing through one of those busier corridors. The thick disk of the galaxy plays a crucial role in this convergence. Unlike the thin disk where the Sun resides, home to younger, metal-rich stars, the thick disk contains ancient stellar populations, survivors from an earlier epoch of galactic history. These stars orbit with different kinematics, tilted relative to the thin disk, moving faster or slower depending on their origins. Their remnants scatter comets and planetesimals, ejecting them into interstellar space where they wander for billions of years. When our solar system's orbit intersects streams from this population, the odds of encountering such wanderers rise dramatically. Astronomers have traced the motion of 3I Atlas backward and found hints that its origin may lie within this ancient thick disk. If true, it means the object began its journey long before our Sun was even born, set adrift from a planetary system orbiting an old, dim star that may no longer exist. Its path is not random, but the product of galactic dynamics, the stirring of stellar orbits, the gravitational tides of spiral arms, the vast mixing that churns the Milky Way like an ocean. Objects like this may cluster in streams, entire families moving together, invisible until one happens to cross our narrow line of sight. The idea of galactic seasons emerges naturally from this. Just as Earth tilts into summer or winter, the solar system's motion through the galaxy brings it into regions where encounters become more likely. A season may last millions of years, but its influence is no less real. One epoch brings quiescence, another a rain of interstellar debris. 3I Atlas, arriving in the wake of Oumuamua and Borisov, may signal that we are in the early days of such a season, a passage through a stretch of galactic road where traffic is unexpectedly heavy. To picture this, imagine rivers converging in a valley. Each river carries sediment of flow from faraway mountains. Separately, they may run unnoticed, thin streams across the landscape. But when they merge, the valley swells with their combined waters, currents overlapping, eddies forming in complex, temporary patterns. Our solar system now finds itself in such a valley where streams of ancient debris, stellar remnants, and galactic dynamics intersect. The result is a brief but potent convergence, a swelling of probability that delivers interstellar wanderers into our awareness. The local standard of rest provides another frame of understanding. This is the average motion of stars and material in our neighborhood of the galaxy, the baseline against which velocities are measured. Our Sun drifts relative to this standard, carrying Earth and its companions slightly askew. Interstellar objects, moving at their own inherited speeds from eons of stellar scattering, pass through this frame like boats cutting across a harbour. When motions align, encounters become less likely, like ships sailing parallel. When motions diverge, crossings increase, like vessels cutting diagonally across crowded lanes. Our relative drift may now place us at just such a crossing angle, raising the odds of meetings with travelers like 3i Atlas. Galactic rotation only adds to the complexity. Stars near the center move faster, those farther out more slowly, and over billions of years, this differential motion shears streams of material into elongated structures. Clusters dissolve, comets scatter, dark matter filaments tug invisibly at their paths. The galaxy is a stirring pot, mixing ingredients without pause, creating temporary alignments where paths intersect. In such turbulence, it is inevitable that fragments cast adrift long ago will occasionally sweep past our vantage. Yet the clustering of 3 detections in under a decade suggests not mere randomness but a confluence of cycles. Cosmic weather patterns extend this metaphor. Density waves within the spiral arms compress gas, trigger star formation, and alter the distribution of matter. Passing through such regions may increase encounters with stellar debris, much as a storm front increases rainfall. Stellar flybys, too, contribute. Nearby stars occasionally brush past the outer edges of our system, disturbing the Oort cloud and sending comets inward. Multiply this by billions of years and thousands of encounters, and the galaxy becomes a living weather system, shaping the timing of every visitor we see. What makes the present convergence remarkable is how many cycles appear to align. The solar system's orbit places us in a neighborhood influenced by thick disk populations. Our relative motion through the local standard of rest increases the likelihood of crossing debris streams. Galactic rotation ensures those streams are elongated and intersecting. Spiral arm dynamics may amplify the density of material. Stellar evolution has scattered objects for billions of years, and those fragments now pass within our reach. Each factor alone might deliver the occasional wanderer. Together, they create a floodplain where encounters become inevitable, like rivers merging, like storms converging, like a traffic pattern at a busy intersection. The galaxy channels its complexity into fleeting alignments. For us, this alignment manifests as 3 visitors in 8 years, a rate that defies older expectations. Perhaps this is coincidence, but coincidence shaped by currents too vast to ignore. We find ourselves not at a random point in time, but at the junction of cycles layered upon cycles, an era when the Milky Way's rhythms bring the distant and the ancient into sudden proximity. The Great Convergence is not static, it is a passage. Just as seasons change, so too will our galactic environment. The streams we encounter now may dissipate, the traffic thin, the visitors grow rare again. Yet for this moment, in this stretch of the cosmic road, the rivers flow together and the crossings are rich. What remains is to ask how perception and technology respond to such a season, how the awakening of our cosmic eyes meets the opportunities of convergence. The convergence of cosmic cycles would have remained invisible if not for the steady sharpening of our instruments. A universe crowded with wanderers means little when the tools of perception cannot tell them apart from the static of stars. The paradox of modern observation lies here. The more capable our telescopes become, the more the universe seems to teem with phenomena once considered rare. Every new leap in detection technology redefines frequency, taking what seemed extraordinary and showing it to be commonplace. Before 2017, interstellar visitors were thought to be curiosities bordering on impossibility. Their calculated rarity was based on what had been seen, which amounted to nothing at all. Then, with the discovery of Oumuamua, the statistical framework collapsed because it became clear that the absence of detections was not evidence of absence, but the artifact of blindness. What we interpreted as cosmic rarity was in truth technological limitation, a failure to perceive rather than a scarcity of events. This realization gave rise to the question of selection bias. Were interstellar visitors always this common, slipping through our skies while generations of astronomers overlooked them? The answer now seems unavoidable. They were not absent. They were simply invisible until the sky was watched in the right way. The modern era of survey telescopes, machines designed to map everything rather than focus on the exceptional, shifted astronomy from selective observation to systematic census. It was this shift that brought the strangers into view. The Zwicky Transient Facility, Neowise, Atlas, Pan-STARRS, and other wide-field sky surveys became the engines of this revolution. Each was built with the capacity to scan vast swaths of the sky rapidly, night after night, cataloguing faint changes that older instruments would have dismissed or ignored. A star brightening, an asteroid streaking, a comet flaring, a transient light source appearing and fading. These became the raw material of discovery. Interstellar objects were not their explicit quarry, but they were swept up in the net, their brief angled motions flagged among millions of points of light. Detection thresholds, however, define what is possible. For an object to be discovered, it must pass within a narrow corridor of brightness and proximity, close enough to register against the background and luminous enough to rise above the noise. Countless others pass unseen, too faint or too distant to leave a mark. 3I Atlas happened to meet the criteria, just bright enough and just near enough for its motion to trigger the algorithms. The lesson is humbling. The catalogue we possess is not a complete record of reality, but a filtered sample, shaped by the sensitivity of our instruments and the diligence of our surveys. Once one anomaly is detected, the cascade of confirmation begins. The discovery of Oumuamua sharpened expectations, proving that interstellar objects could be found and catalogued. That proof primed observers to recognize Borisov in 2019 and later Atlas in 2025. Awareness itself acts as a multiplier. Astronomers now know to look for the peculiar velocities, the unusual orbital signatures, the hyperbolic paths. Finding one made finding others more likely, not because the universe changed, but because human perception and methodology adapted. The process carries within it the imprint of observer bias, what some call the streetlight effect. We search where our lamps are brightest, mistaking visibility for prevalence. A drunkard looks for lost keys beneath a streetlight, not because the keys must be there, but because that is where the light falls. So too with astronomy. Our discoveries cluster in the zones we can see, the wavelengths we can measure, the brightness levels our instruments can capture. Interstellar objects are not rare beneath the light, they are only detectable there. Beyond the reach of our glow, countless others roam uncounted. This recognition reshapes the meaning of cosmic timing. The sudden appearance of 3 objects in 8 years is not solely a galactic coincidence, but also a reflection of the streetlight expanding. As surveys widened, as computational pipelines grew stronger, as follow-up telescopes coordinated globally, the effective glow of our lamps spread across the sky. The sidewalk did not suddenly fill with strangers. Our vision finally illuminated them. Yet the question lingers: how many more are inbound, already slipping silently through the outer solar system, waiting to become bright enough for us to notice? Predictions vary, but the consensus grows that dozens may be visible within the coming decades, perhaps more once the Vera Rubin Observatory begins operations. Designed to scan the entire visible sky every few nights with unprecedented depth, Rubin will push the threshold further still, transforming the rare into the routine. The implication is profound. Interstellar visitors may become a steady stream, catalogued as easily as asteroids and comets are today. The metaphor of magnification captures this transformation. For centuries, we examined the night with the equivalent of a magnifying glass, focusing on individual stars, singular planets, exceptional novae. Each discovery was extraordinary because it was rare to our instruments. Now the magnifying glass has been replaced with a microscope, a device that reveals entire worlds of structure previously invisible. The fabric of the sky itself changes under this scrutiny, details unfolding where once there was only blur. What looked empty becomes crowded. What looked rare becomes common. What looked exceptional becomes inevitable. This feedback loop, technology enabling discovery, discovery reshaping perception, perception driving further technological leaps, propels astronomy forward. With every advance, the definition of normal shifts. To us, interstellar objects feel like novelties. To future generations raised under the watchful gaze of Rubin and its successors, they may feel as ordinary as falling stars. The extraordinary is always a function of what can be seen. The universe does not change, but the clarity of our gaze does, pulling more and more of its secrets into the light. The widening glow of our street lamp now reveals what once hid in the shadows. The question, then, is not whether the visitors are rare, but how long this season of clarity will last, and what patterns may emerge as more and more of them step into view. The widening glow of our searchlights tells us how to see, but the story of Three-Eye Atlas stretches far beyond our own ability to perceive. This visitor is not a child of the modern era, nor even of the last few galactic cycles. It has been on its journey for billions of years, long before mammals rose on Earth, before the continents formed their present shapes, before our sun itself came to life. To understand its arrival, one must turn to the clockwork of stellar generations, the slow heartbeat of the galaxy itself. When Three-Eye Atlas was born, the Milky Way was a younger, more restless place. Stars blazed into being at a faster pace, their nurseries dense with gas and dust. These were the epochs when the galaxy's thick disk took shape, populated by stars older than our sun, their compositions bearing the chemical scars of early times. Such ancient stars belong to what astronomers call population 2, metal poor, forged before the galaxy had been enriched by countless cycles of stellar death and rebirth. Around them, debris fields coalesced, icy remnants locked into orbits, destined to be scattered into the interstellar dark by gravitational disturbances. The thick disk provides a crucial clue. Its stars move with dynamics distinct from the younger thin disk where our sun resides. Their paths are tilted, their motions less orderly, their populations older by billions of years. If Three-Eye Atlas carries the fingerprint of that region, it suggests that this comet formed in an environment profoundly different from the one that shaped the comets of our Oort cloud. Its chemistry, its density, even the balance of volatile ices it carries may hold the record of an earlier epoch in galactic history. Each molecule is a fossil, telling of the state of matter in the days when the Milky Way was still assembling itself. In those formative eras, the galaxy was alive with violence and change. Massive stars lived brief, furious lives, expelling heavy elements in titanic supernova. Black holes grew at the core, stirring their surroundings with bursts of energy. Planetary systems were born and unbound in quick succession. It was in such turbulence that icy bodies like Three-Eye Atlas were cast adrift, children of primordial systems flung into the depths of interstellar space. Their journeys began not with quiet ejection, but with cataclysm, a star's shifting gravity or a sibling planet's pull tearing them from their home and setting them loose across the galaxy. The diaspora of stars was mirrored by a diaspora of their debris. As stellar clusters dissolved, their planets and comets were scattered like seeds. Some remained bound within distant shells around their suns, but others were ejected entirely, their orbits stretched beyond recovery, their trajectories carrying them into the void between stars. For every star that perished, countless fragments were cast outward, joining an invisible current of material threading through the galaxy. Over billions of years, these objects accumulated into a vast, unseen population, silent travelers enduring epochs that make human history seem less than a blink. This scattering created the conditions for convergence. Old comets, long divorced from their birth systems, drift in streams shaped by gravitational tides. Just as a river may carry logs together in clusters, galactic forces can align these ancient fragments into loose families that move through space with shared velocities. Their origins lie in the same stellar neighborhoods, their destinies guided by the same gravitational influences. When one enters our solar system, others may follow in time, not as deliberate company, but as the statistical echo of common ancestry. To think of 3i Atlas in this way is to see it as part of a lineage, not a singular oddity. Its journey is the culmination of ancient stellar rhythms, stars forming, burning, and dying, scattering their remnants to the galactic winds. Each stellar generation alters the composition of the next, enriching the medium with heavier elements, changing the kinds of planets and comets that can form. To hold such an object in our gaze is to witness the fossil record of an earlier universe, to touch the chemistry of stars long extinguished. The clustering of such objects may be a kind of gravitational archaeology. By studying their trajectories and compositions, astronomers can reconstruct the histories of their parent systems, tracing backward to the conditions of star formation in the thick disk. They are like shards of pottery uncovered in a forgotten city, fragments of a culture long vanished, yet still carrying its mark. 3. Atlas does not simply pass through our system. It brings with it the signature of an age when the galaxy was young and restless, when stellar families were torn apart and their children cast into exile. The scale of time involved defies human comprehension. Billions of years ago, while Earth was still molten and uninhabitable, this comet was already adrift, its path determined by encounters that predate our planet's existence. While continents drifted and oceans formed, while life clawed its way from single cells to forests and vertebrates and finally intelligence, 3i Atlas continued unperturbed, crossing gulfs of space with the patience of eternity. Its entry into our skies is not the beginning of a story, but a fleeting intersection, a brief overlap between its billion-year odyssey and the span of our observation. From this perspective, its arrival now feels less like chance and more like resonance. Multiple cycles, stellar generations, galactic orbits, planetary histories have overlapped in this moment. The comet's release from its parent star billions of years ago, its long drift through the galaxy, our sun's current position in its orbit, the readiness of our instruments to detect such a faint traveler. All of these independent rhythms align here, in the early 21st century, in the gaze of human beings. The rhythm of stellar generations beats slowly, but its echoes reach us in profound ways. To watch 3i Atlas approach is to listen to a note struck billions of years ago, still resonating across the galaxy. It is a message without intent, a byproduct of cosmic community, yet one that allows us to glimpse the deep continuity between the lives of stars and the fragments they leave behind. As more of these ancient wanderers step into the circle of our perception, we begin to see not isolated anomalies, but the contours of a larger symphony, one that plays across billions of years and ties our present moment to the forgotten past of the Milky Way. Their arrivals, one after another, suggest a tempo we are only beginning to recognize, a cadence written into the galaxy itself. What was once invisible now resolves into pattern, a rhythm not of our making, but one we have finally grown capable of hearing. The rhythm of stellar generations explains much, yet still a deeper question lingers. Why now, in such tight sequence, do these visitors arrive within the span of a single human lifetime? Gravitational lensing provides a tantalizing analogy. Just as a massive cluster can bend light into arcs, magnifying galaxies far behind it, so too might concentrations of dark matter act as lenses for matter itself. Comets, like 3i Atlas, drifting for billions of years, could have their courses subtly bent and refocused, herded into streams that intersect with the solar system. Their arrivals would then be less random encounters and more the product of unseen guidance, the result of cosmic optics at scales we are only beginning to imagine. Beyond lensing lies the influence of the local group itself. Our galaxy, bound with Andromeda and dozens of smaller companions, drifts within a shared halo of dark matter. This shared reservoir exerts a gravitational influence on everything within it. shaping the flows of both stars and smaller debris. The comets now arriving could be responding not only to the sun's pull, but to the collective gravitation of the local group, funneled along pathways laid down by the invisible scaffold of dark matter that surrounds us. The metaphor of unseen currents is irresistible. Sailors navigate oceans by watching winds and tides, even if they cannot see the forces themselves. In similar fashion, interstellar comets may be the driftwood of cosmic seas, carried along by dark matter streams. We see only the fragments that washes ashore in our solar system, but behind them may be an entire tide of material moving in synchrony. If so, their arrival is not a surprise, but part of a larger pattern that remains hidden until mapped. Such a theory carries bold implications that the universe may possess a predictable highway system, an infrastructure carved not in stone or steel, but in gravity itself. These highways would not be visible lanes, but gradients of mass distribution, corridors where the odds of encountering travelers increase dramatically. In this framework, Y Oumuamua, 2I Borisov, and 3I Atlas are not statistical flukes, but the first hints of a larger flow, pioneers appearing at the edges of a current we have only just begun to notice. If these highways exist, then future arrivals could be forecast not by chance, but by modeling the hidden structure of dark matter around us. Just as meteor showers recur when Earth passes through the debris stream of a comet, so too might interstellar object showers occur when our solar system intersects with dark matter filaments channeling ancient debris. Predictability would replace coincidence, transforming mystery into expectation. The speculative framework demands a shift in perception. The universe may not be random chaos, but a system of resonances, alignments, and channels, with dark matter shaping traffic patterns at scales far beyond our intuition. These highways would be as real as the spiral arms of galaxies, yet hidden from sight, detectable only by their influence on the movement of stars and the sudden appearance of visitors in our sky. To walk through the streets of a city is to encounter strangers more often at intersections. Perhaps our solar system now drifts through such a cosmic crossroads. The thought is both humbling and exhilarating, that every interstellar visitor we see may be more than a solitary traveler. Each might be the herald of a greater convergence, a sign that we are crossing into a region of space where invisible structures concentrate the flotsam of ancient stars. The pattern could stretch far beyond the lifetimes of civilizations, written into the deep geometry of the universe itself, waiting for eyes sharp enough to trace its lines. The highways of dark matter remain only a theory, but the evidence grows each time a wanderer appears. To recognize such a system would be to admit that our solar system's encounters are not isolated or accidental, but part of a grander choreography, one whose music plays in frequencies we are only beginning to hear. The next visitor may not just be another anomaly, but a note in a deeper melody, a resonance between the visible and the invisible, between the matter we know and the matter we can only infer. The speculation about hidden highways leads naturally into another, more unsettling layer of the mystery. Why do these arrivals happen precisely at a moment when we are capable of noticing them? For billions of years, comets like 3I Atlas must have been drifting silently through the void, slipping past our sun unseen. Yet, only in the last few years of human history, a blink in cosmic time, have we built the tools to catch them in the act. The coincidence is startling, almost too perfect, raising the possibility that the real explanation lies not in the cosmos alone, but in the relationship between the universe and its observers. This is the essence of the anthropic timing principle. It asks whether the significance of these interstellar visitors depends not just on their arrival, but on our ability to witness them. If no one had been watching in 2017, Oumuamua would have come and gone as countless others surely did. Its hyperbolic path would have left no record. The same is true for Borisov and even Atlas today. Their presence only matters because a species at just the right stage of development happened to be paying attention. Civilization exists in a narrow detection window. For most of human history, we lacked the instruments to find such faint, fast-moving objects. A telescope in Galileo's hand could never have spotted Oumuamua at its approach. Yet fast forward to the far future, when humanity perhaps spreads across the stars, and such arrivals may lose their wonder. Interstellar travelers will be as ordinary as drifting icebergs to a sailor. Our moment, the present age, is unique because we have just enough technology to perceive these visitors, but not so much that their presence feels mundane. We stand at the intersection of curiosity and limitation, where the arrival of each object still strikes us as a revelation. Placed in the larger frame of cosmic history, this window looks vanishingly thin. The universe is 13.8 billion years old. Our species has existed for a mere few 100,000 years, and our ability to scan the skies with automated precision telescopes stretches back only a handful of decades. The chance alignment of these interstellar visitors with the infancy of our detection capability seems almost absurd, as though the cosmos arranged a curtain to lift just as we happen to look up. The anthropic interpretation suggests that perhaps the curtain was always lifting in this way, but no one was in the audience until now. Out of all the billions of years in which comets like 3I Atlas could pass by unnoticed, only during this tiny sliver of time could a conscious observer with the right tools exist to assign meaning to the timing. In this view, the mystery is not why the visitors come now, but why we exist now to see them. Such reflections fold back onto the Fermi paradox, the haunting silence that echoes when we ask why no other civilizations are visible in a galaxy that should teem with them. Perhaps the silence is misleading. Perhaps civilizations like ours are simply rare, emerging in brief windows of detection capacity, each one seeing its own handful of interstellar visitors and wondering whether the timing is significant. What feels like a profound cosmic convergence may, from another vantage point, be the inevitable perception of any species just reaching the threshold of awareness. The universe does not change for us, rather, our awareness makes it appear to. Yet the philosophical implications run deeper still. To notice an object like Atlas is to participate in the universe observing itself. Consciousness is not separate from the cosmos, but a product of its evolution. Our minds are born of ancient stars, forged from atoms created in supernovae, shaped by planetary systems born billions of years ago. To now watch an interstellar traveler pass through our skies is to witness a reunion, matter recognizing matter across unimaginable stretches of time and space. The timing feels perfect because it is not separate from us, it is us. This perspective reframes coincidence as inevitability. Of course, we notice interstellar objects now, because now is the only time we could. Before, we lacked the eyes. Later, we may have moved beyond surprise. The meaning of now is not random, but conditioned by our existence within it. Just as a flower blooms in spring rather than winter, so too does awareness emerge at its proper season. The arrivals of Oumuamua, Borisov, and Atlas are petals in that bloom, visible precisely because our species has ripened into the stage of watching. The anthropic timing principle does not diminish the wonder of the moment. It heightens it. If anything, it transforms these comets into symbols of our place in cosmic history. The coincidence is no longer an accident, but a mirror, showing us the delicate balance between capability and mystery, perception and event. We gaze upward, not simply at an icy body hurtling through space, but at the evidence that our consciousness is tuned to the precise frequency of discovery. Perhaps this is why the arrivals feel almost theatrical, as though staged. The choreography is not the dance of objects alone, but the synchronized step of object and observer, comet and civilization. To be alive now, with eyes to see, is itself the improbable alignment. The visitors are not knocking at our door, rather, we have just built a door and discovered that the universe has been passing by it all along. Each interstellar comet we glimpse is therefore a message about ourselves. It tells us not only about the chemistry of distant stars, but about the brevity and importance of this window of awareness. It whispers that we are young, that we are fragile, and that our curiosity arrives precisely when the universe offers material to feed it. Consciousness, in this frame, is not an accident of evolution, but the inevitable flowering of matter becoming aware of its own ancient journeys. The timing principle leaves us standing in wonder, asking not merely why these objects come now, but why we exist now to see them. It casts human civilization as a flicker in the cosmos that nonetheless matters, because in this flicker the universe perceives itself, recognizes its own hidden architecture, and assigns meaning to encounters billions of years in the making. The dance of ice and light across the heavens becomes inseparable from the dance of thought within our minds. The next step is to ask whether this perfect timing is itself part of a larger pattern, not of perception alone, but of the forces shaping the universe into cycles of convergence. If the anthropic principle tells us why we see the visitors now, another layer may yet reveal why the visitors themselves cluster in this season of our galactic journey. The suggestion that consciousness tunes itself to timing still leaves unspoken the role of the stage upon which these encounters unfold. Our solar system is not a passive backdrop, waiting idly for travelers to wander in. It exerts its own influence, pulling, bending, and sometimes amplifying the chances that an object like 3I Atlas will cross into our awareness. The hidden architecture of our neighborhood shapes not only what arrives, but how it becomes visible, casting the sun and its planets as quiet conspirators in the drama of timing. The most obvious agent in this gravitational theatre is Jupiter. Massive beyond easy comparison, it outweighs every other planet combined, a colossus whose reach extends far beyond its own orbit. Its gravity acts as both guardian and gatekeeper. On one hand, it shields Earth by intercepting or ejecting threatening asteroids. On the other, it funnels passing bodies inward, nudging their paths into orbits that bring them closer to the Sun. To a traveler like 3I Atlas, the pull of Jupiter is not a subtle force but a decisive hand on the tiller, one that can redirect trajectories by millions of miles. It is no accident that so many comets, interstellar or otherwise, enter our skies through gravitational corridors widened by Jupiter's presence. Equally influential is the geometry of the ecliptic plane. The planets, born from the same disk of dust and gas, orbit the Sun in a broad, flat alignment. Interstellar visitors crossing the solar system often encounter this plane, their paths drawn into predictable alignments where detection is easier. To astronomers scanning the skies, this is a gift of order amid chaos. The visitors' orbits may be hyperbolic, their origins interstellar, but their intersection with the ecliptic gives us a stage upon which to observe them. Without this advantage, many would streak past unnoticed, lost in the vastness above or below the plane where our instruments do not linger as long. The Sun itself amplifies these opportunities through a subtle but extraordinary phenomenon: gravitational lensing. Just as a glass lens bends light to magnify distant objects, the Sun's immense gravity bends space-time, focusing not only photons but the paths of matter itself. A comet drifting near the Sun does not simply pass by. Its trajectory is curved, its speed altered, its visibility enhanced by the luminous backdrop of the star. To us, this lensing effect transforms the Sun into a cosmic telescope, turning invisible wanderers into brilliant streaks against the night. Beyond the planetary realm lies another boundary of influence: the heliosphere. This vast bubble, inflated by the solar wind, marks the frontier where the Sun's domain meets the interstellar medium. At this invisible edge, charged particles clash, magnetic fields warp, and cosmic rays shift their course. For small, icy bodies traveling through it, this region is a gauntlet of subtle forces. The solar wind pushes against their surfaces, altering spin or shedding gas. Magnetic turbulence may nudge their trajectories just enough to bring them closer to the inner solar system where telescopes wait. The heliosphere is not merely a shield but a threshold, filtering and shaping what enters from the galaxy beyond. Even Earth itself plays a role, not through gravity alone, but through the rhythms of its orbit. Our vantage point changes with the seasons, shifting the direction in which we look. The window for visibility is narrow, dependent on the choreography of both the visitor and the observer circling the sun together. Layered upon these gravitational and orbital factors are the subtler influences of magnetic fields and stellar winds. Our sun's outflow interacts with charged dust and icy fragments, sometimes accelerating them, sometimes slowing them, always reshaping the smallest details of their motion. Over billions of years, such whispers of force can accumulate into decisive changes. A traveler like 3I Atlas, influenced countless times by faint nudges across the galaxy, may find its final course determined by the sun's magnetic breath. What appears to us as coincidence may be the outcome of countless invisible adjustments, each one tipping the scales toward arrival. In this sense, hidden attractors abound. They are not visible in the way a planet is, but their presence is undeniable in the statistics of what we see. Resonances, gravitational corridors, magnetic flows, each acts as a guide, shaping probability into path. The result is a landscape of invisible highways and funnels within our own solar system, channels that magnify the odds of encounter. We imagine interstellar comets as wanderers, yet in truth they are dancers moving to music we cannot hear, choreographed by forces both local and cosmic. Taken together, these influences cast the solar system not as a passive stage, but as a beacon. Jupiter pulls, the ecliptic aligns, the sun lenses, the heliosphere filters, and Earth's orbit grants us the vantage point to see. To an object drifting in the galaxy, our neighborhood may appear as a lighthouse shining across interstellar darkness. Its beacon is not light alone, but gravitational presence, magnetic reach, and orbital geometry, all conspiring to make encounters possible. Travelers passing nearby are drawn not at random, but toward the glow. The thought carries a startling implication. If our solar system truly acts as a lighthouse, then it is not surprising that we see visitors clustered in time. We are not stumbling across accidents. We are standing in the light we ourselves project, illuminated by forces written into the architecture of our system. The arrivals of Oumuamua, Borisov, and Atlas may be signals not only of galactic currents, but of our own gravitational presence broadcasting across the void. What appears to us as coincidence may, in truth, be the reflection of our own structure, the way the universe bends around us, and the way we bend around it. The hidden influence of the solar system transforms wanderers into witnesses, making their paths converge upon our skies. To see them is to glimpse not only their journeys, but the quiet power of our own. The question that follows is whether this beaconing effect extends further than we imagine. The suggestion that our solar system serves as a lighthouse raises an unsettling yet profound question. If our very structure summons these travelers into visibility, then perhaps their timing is not just coincidence, but communication. The universe does not speak in words, but in arrivals, in rhythms, in alignments that, when recognized, become messages waiting to be read. What seems at first a random visitation may instead be a clue to galactic architecture, an encoded signal in motion that whispers of ancient epochs and hidden structures. Pattern recognition lies at the heart of this inquiry. Astronomers are not simply watching streaks of light across the sky. They are searching for cadence, for the invisible metronome that dictates when and where such visitors appear. A single detection might be chance, two perhaps coincidence, but three or more force the question of structure. The intervals between appearances, the directions of approach, the velocities relative to the galactic frame. They hint at the scaffolding of the Milky Way, the unseen bridges between stellar populations, and the corridors shaped by gravitation and dark matter alike. Timing becomes a cipher, and we are only now learning to read its symbols. Yet even as we decode, we must remember the sampling effect. For every interstellar object that swings into view, millions slip past unnoticed, their faintness or distance hiding them from our telescopes. The ones we see are not the majority, but the survivors of statistical filtering, rare ambassadors chosen by circumstance. Each detection is thus a weighted lottery, a tiny sample plucked from an ocean of invisibles. In this sense, our observations resemble archaeology conducted with fragments, a shard of pottery here, a chipped blade there, enough to reconstruct a civilization long gone. Every passing object is such a shard, preserving in its motion and composition the imprint of stars that lived and died. This is why 3I Atlas carries a significance beyond its brief passage. Its origin in the thick disk places it among the oldest relics of the galaxy, debris flung outward during an era when star formation surged with a vigor now long diminished. To study its path is to glimpse the motions of ancient stellar populations whose kinematics differ from the younger stars of the thin disk that now dominate our skies. To probe its chemistry is to touch the ashes of stellar furnaces that enriched the galaxy more than 7 billion years ago. Within its ice may be locked isotopic fingerprints, the byproducts of primordial nucleosynthesis preserved against the erosions of time. Imagine then this comet as a time capsule launched before Earth itself condensed, drifting across the galaxy as empires of stars rose and faded. The dust within it remembers the abundance of heavy elements in its birth cloud. The frozen volatiles remember the radiation environment. The trajectory remembers the gravitational tides that once tossed it free of its home system. Each detail, if decoded, becomes a message, not written for us, yet awaiting us all the same. Such objects transform astronomy into a form of cosmic archaeology. Where rocks and fossils preserve Earth's history, these visitors preserve the history of the galaxy. Their timing is not only their arrival into our skies, but also their delivery from the deep past into the present moment. We are not merely seeing an interstellar comet, we are receiving a messenger that has traveled longer than multicellular life has existed on Earth. Its appearance now, precisely when our instruments can detect and study it, collapses billions of years into a single night of observation. The messenger hypothesis takes this further. It suggests that interstellar objects themselves act as carriers of cosmic information, whether intentionally or not. They are couriers of chemistry, of dynamics, of history encoded in frozen shells. To us, they are messengers precisely because of their timing. Only now, in this sliver of cosmic chronology when we are capable of recognition, do they become legible. A visitor arriving 100 million years ago would have burned unnoticed across empty skies. A visitor arriving 100 million years hence might find an Earth transformed or uninhabited. The message matters only when there is someone able to receive it. Such timing sharpens into a philosophical blade. Perhaps the arrivals of these objects are not remarkable because they happen now, but because only now can they be observed. This transforms timing itself into information, a reminder that the universe can be read only at particular moments, when the observer and the observed overlap in capability. Just as fossils mean nothing to a creature without memory, interstellar messengers mean nothing to a world without telescopes. To us, however, they are not silent. They are eloquent, their arrival rhythm carrying the weight. Each appearance tells us not only of the object itself, but of the structure from which it came. Borisov, Oumuamua, Atlas, each emerged from different stellar nurseries, different populations, different galactic epochs. Together, they form a mosaic that over time may map the skeleton of the Milky Way in a way no star catalogue alone could achieve. Timing becomes the axis upon which cosmic archaeology spins. By aligning detections with galactic motion, by noting the clustering of arrival vectors, by comparing chemical signatures across epochs, we may reconstruct the evolution of our galaxy through the chance encounters of wandering debris. The universe, in this light, is not silent but richly communicative, though its messages arrive in bottles cast across oceans of time. Each interstellar object is one such bottle, sealed with ice, inscribed with isotopes, delivered by orbital mechanics into our waiting nets. The timing of its arrival is part of the message, a reminder that history is not static but dynamic. The question grows more daring when one considers scale. If the timing of arrivals can encode galactic history, could it also encode patterns of larger structure, streams shaped by dark matter, tides from satellite galaxies, influences from the local group itself? The arrivals we see may be fragments of a grander rhythm, the pulse of cosmic infrastructure manifesting in icy travelers. Recognizing that rhythm would transform not only our understanding of comets, but our understanding of the galaxy itself. Timing, then, is not incidental. It is the key by which the lock of deep time is opened, the measure by which we transform scattered arrivals into coherent history. Without timing, a visitor is merely an icy rock. With timing, it becomes a messenger of galactic past, a clue to processes far larger than itself. The possibility now stretches before us, that each arrival, each detection, is less a random accident than a note in a galactic symphony, its melody only now audible because we have built the instruments. What awaits is not just the next object, but the next measure in a song that has been playing for billions of years. If each visitor is a note in a galactic symphony, then the melody is only beginning to emerge. What once felt like singular anomalies, Oumuamua in 2017, Borisov in 2019, Atlas in 2025, now appear as the opening bars of a composition that may soon grow louder, richer, impossible to ignore. Astronomers are preparing for a future where interstellar detections will not be measured in decades, but in months, perhaps even in weeks. The trickle is about to become a flood, not because the galaxy has changed, but because our eyes have finally opened wide enough to see what has always been there. Predictions suggest that in the coming decade, the number of confirmed interstellar visitors could grow into the dozens, perhaps even the hundreds. Each one will carry a unique trajectory, a unique chemical story, a unique timestamp in the history. The confidence of these forecasts comes not from speculation, but from the technological revolution now underway. Telescopes capable of scanning vast regions of the sky nightly are no longer dreams. They are being built, calibrated, and prepared to stare into the darkness with relentless precision. The Vera Rubin Observatory represents the most dramatic leap. With its legacy survey of space and time, it will record the entire southern sky every few nights, creating a dynamic atlas of motion and change. Where older surveys saw faint specks, Rubin will track billions of objects with unprecedented clarity. Its cameras will generate 20 terabytes of data every single night, a torrent so immense that algorithms must shoulder the burden of discovery, flagging unusual trajectories faster than any human eye could. Within that flood of information, interstellar visitors will no longer slip by unnoticed. Their hyperbolic paths will stand out like signatures written in fire against the slow waltz. This coming avalanche of data means that astronomy will soon enter an age of cataloguing the galaxy's messengers. Instead of 3 lonely entries in the record books, We may soon have an interstellar object catalogue containing dozens of confirmed travelers, each cross-referenced by orbital path, velocity, spectral signature, and origin vector. Such a database will not merely list curiosities, it will reveal patterns. If multiple objects cluster in approach direction, that may indicate a stream born from the same ancient stellar nursery. If chemical compositions repeat across visitors, that may expose the common fingerprints of galactic evolution. What once seemed like coincidences will resolve into constellations of meaning. Trajectory analysis will extend this transformation even further. With more detections, astronomers will begin predicting arrivals in advance, projecting the paths of faint objects long before they swing close to the Sun. Instead of reacting in surprise, humanity may soon anticipate encounters years before they occur. We may know in 2028, for example, that an interstellar comet will blaze brightest in 2032, its orbit mapped with enough certainty to plan observation campaigns well ahead of time. The randomness of discovery will be replaced by the cadence of scheduling. This anticipation opens a possibility that once belonged only to science fiction: interception. For the first time, space agencies will have the lead time required to design missions not just to observe from afar, but to send probes directly into the paths of these visitors. The narrow window of close approach will no longer be a limitation, but an opportunity, a corridor for spacecraft to rendezvous with matter that has traveled across the galaxy. Instead of distant telescopic spectra, we may retrieve samples, images, and measurements taken from a few hundred kilometers away, or even carry fragments back to Earth. To stand on Earth holding a rock that formed around another star billions of years ago would be to hold the galaxy itself. Such missions will demand precision, courage, and international collaboration, for the objects move fast, faster than anything native to our system, and the timing must be perfect. But with predictions in place, the dream of interstellar sample return is no longer unimaginable. It is an engineering problem awaiting the right moment of convergence. Cosmic timing itself may become a tool in this era. By analyzing when and how visitors appear, astronomers will map not only the galaxy's composition, but its structure in motion. Just as rainfall patterns reveal the shape of mountain ranges, the arrival patterns of interstellar objects may reveal streams of matter sculpted by the invisible skeleton of the Milky Way. Each detection sharpens the contour of those hidden structures, allowing us to reconstruct the unseen highways of debris flowing through our neighborhood of the galaxy. The convergence lies not only in data, but in capability. We stand at the intersection of detection and interception, where the ability to see aligns with the ability to act. For the first time in cosmic history, a species exists that can both recognize an interstellar visitor and consider meeting it face to face. The next decade will not just expand our catalogue of cosmic messengers, it will present us with the choice of whether to greet them as distant curiosities or as opportunities for direct encounter. The flood is coming. The question is whether we will be ready to step into it, nets in hand, prepared to gather the messages carried across billions of years of galactic drift. The notion of readiness is not merely a matter of engineering. It is the result of countless convergences, threads of cosmic circumstance weaving together into a single tapestry that could not exist at any other time. Technology, orbital position, stellar dynamics, and even the rise of consciousness itself have synchronized in a way that makes the present moment extraordinary. The appearance of 3I Atlas is not only about a comet on a hyperbolic trajectory, it is about all the cycles, seen and unseen, that allow us to notice it, study it, and contemplate its meaning. Consider first the technological dimension. For billions of years, interstellar visitors must have entered our skies unseen, streaking past with only the night air as their witness. The creatures that once roamed Earth, the trilobites, the dinosaurs, the mammoths, lived under skies where such travelers came and went without consequence. Only now do we have instruments sensitive enough to register them. digital sentinels that scan the heavens every night with mechanical patience. The invention of wide-field surveys, automated pipelines, and global telescope networks has coincided precisely with the moment when our attention has turned outward in earnest. Without this alignment, Atlas would remain invisible, lost among the stars. Yet technology alone cannot account for the timing. Our solar system occupies a position in both space and time that makes detection possible. We orbit not too close to the violent galactic center, nor too far in the barren outskirts, but within what some call the galactic habitable zone. It is here, in this temperate band of the Milky Way, that life arose, evolved, and at last built eyes capable of perceiving beyond the sun's domain. If Earth had formed elsewhere, or later, or within a harsher stellar neighborhood, the conditions for both life and technology might never have converged. The rare Earth hypothesis becomes sharper under this lens. It is not merely the right ingredients of water, carbon, and atmosphere that matter, but the timing of encounters with the broader cosmos. Life-bearing worlds may be exceedingly rare, not only because of their fragile conditions, but also because the window of observation is so narrow. Civilizations that rise too early lack the means to detect. Those that rise too late may find the opportunities long past. That we exist now in the slim overlap where both visitors and observers align intensifies the improbability of our vantage. This improbability grows deeper when we consider the cycles of galactic time. 3I Atlas is a messenger born in the galaxy's youth. Its icy body formed when ancient stars were still carving elements from hydrogen and helium. It has traveled for billions of years across spiral arm crossings through density waves brushed by the gravity of passing stars. Its release into our solar neighborhood is not simply a random event. It is the culmination of cosmic processes that began long before Earth itself took shape. For that journey to intersect with a moment when telescopes stand ready and minds question meaning is to recognize timing as the very core of significance. Multiple coincidences create a single opportunity. Our solar system's orbit has brought us through a region dense enough to channel such objects inward. Our instruments have matured enough to detect them. Our species has developed language, science, and cooperation at a scale sufficient to interpret them. Each thread alone might appear ordinary, but woven together they form a confluence so improbable it feels deliberate, though no intent need exist. This is what might be called the observatory effect. We are not passive residents of the galaxy, but active witnesses, existing at exactly the right moment to see the dance of interstellar travelers. Consciousness itself becomes the final converging factor. Without the mind to recognize significance, no timing would matter, no arrival would carry meaning. The comet would sweep by as silent as it has for eons, an unnoticed traveler against a blank sky. With consciousness, however, its passage becomes story, symbol, message, a reminder that awareness transforms motion into revelation. Such timing may even be evidence of deeper patterns within the universe's evolution. Just as life on Earth depends on the synchronization of seasons, tides, and chemical reactions, so might cosmic observation depend on cycles we have yet to understand. The clustering of arrivals, the readiness of our instruments, the alignment of our galactic orbit. Perhaps these are not scattered coincidences, but resonances within a larger system. The universe may not only evolve matter and energy, but moments of recognition. To stand within such a window is to face the profound improbability of our existence. Against the backdrop of 13.8 billion years of cosmic history, we occupy a brief interval when both visitors and observers coincide. The dinosaurs saw no comets from the thick disk. The trilobites had no telescopes to watch for hyperbolic paths. Countless civilizations may have perished on distant worlds before their skies opened wide enough. Yet here we are, at the intersection of cosmic cycles and human readiness, watching as ancient messengers streak into the light. The improbability is not a reason to dismiss, but to listen more closely. For if timing is meaning, then we must treat these arrivals not as trivial curiosities, but as moments where the universe speaks in its own language of motion, resonance, and convergence. The message is not written in words, but in coincidence itself, in the alignment of technology, position, cycle, and consciousness. It is within this confluence that the true weight of interstellar visitors rests. They are not only rocks and ice wandering in from the dark, but confirmations that we live in an age of seeing, that our position in space and time is as rare as the objects themselves. The next messenger will arrive, and another after that, each reinforcing the improbable truth that we are awake exactly when the cosmos chooses to reveal itself. The improbable alignments that brought us to this point demand not only analysis, but reflection. All the cycles of stars and galaxies, the engineering of human hands, and the fragile emergence of awareness have converged on this fleeting present. The answer to the question, why now, does not lie in a single equation, but in the chorus of cosmic rhythms that have met at our doorstep. It is this confluence that makes the moment not only statistically strange, but profoundly meaningful. 3II Atlas is racing inward, a 7 billion-year-old fragment of the galaxy's youth heading toward its October 30th, 2025 rendezvous with the Sun, where it will pass at 1.4 astronomical units. The precision of its trajectory feels uncanny, yet the mathematics of hyperbolic orbits make the improbability real. This object will never return. On December 19, 2025, it will come within 167 million miles of Earth, offering a brief window of observation before it vanishes forever into the dark. To witness such a passage at the exact moment when our instruments are capable of seeing it and our minds are prepared to question it is itself an extraordinary event. The deeper truth suggested by this convergence is that timing reveals hidden architecture. The universe may not arrange its movements with purpose, but the synchronization of arrivals, detections, and awareness exposes structures otherwise invisible. Just as a pendulum reveals gravity's constant pull, so these rare visitors reveal something of the galactic cycles, the dynamics of stellar populations, and the subtle orchestration of space itself. Timing, in this sense, is not incidental. It is diagnostic, a language through which the cosmos quietly speaks. Every moment is an intersection of billion-year journeys. The comet itself was born when the galaxy was still young, perhaps in the disk of a long-dead star whose elements seeded future generations. Its release into interstellar space may have been triggered by gravitational nudges millions of years ago, each influence accumulating into the path we see now. Meanwhile, Earth's own history unfolded across epochs, oceans forming, continents drifting, species evolving, civilizations rising. For their timelines to meet here, in the awareness of a single generation, is the very essence of cosmic choreography. Such choreography is a gift. Perfect cosmic timing is the moment when mysteries step into the light, when chance encounters reveal the vast systems that normally operate beyond perception. Before 2017, interstellar visitors passed us unseen. After our brief window closes, they may continue to pass long after our species has gone. But right now, within this narrow band of awareness, we exist in the overlap between invisibility and indifference, between ignorance and transcendence, where the secrets of the universe can actually be glimpsed. To realize this is humbling. We are witnesses to a performance whose scale dwarfs everything we know, yet whose movements are measured down to the minute. Jupiter's gravity bends paths, the ecliptic plane channels approaches, solar radiation shapes tails, and telescopes record traces, all so that one fragile species can register its presence. The spectacle is not designed for us, yet it resonates as though we were invited, as though our role were always to notice, to recognize, to to give meaning. The humility deepens when we accept that this is not the first time nor the last, but it is our time. We live in the brief window when mysteries become visible. For the dinosaurs, no such moment existed. For the civilizations that may rise after us, the chance may have already passed. Only here, only now, do billions of years of travel converge with decades of technology and a spark of awareness that asks questions large enough to matter. Perhaps that is why this moment feels like a message, not in the sense of deliberate communication, but in the sense of resonance, patterns aligning in ways that awaken recognition. Perhaps the universe does not send messengers randomly. Perhaps it waits until the recipient is ready, until the eyes are open. The data remain essential. Discovered July 1st, 2025, at 420 million miles from the Sun. Perihelion October 30th, 2025, at 1.4 AU. Closest Earth approach, December 19th, 2025, at 167 million miles. An age of 7 billion years written into its frozen body. A galactic orbit of 230 million years carrying us to the place where paths cross. These numbers are not merely statistics but coordinates in the choreography, points along a score written in physics and time. They anchor wonder to reality, allowing us to measure what might otherwise seem ineffable. From here, the choreography continues. The comet will sweep through the inner solar system, brighten as sunlight vaporizes ancient ices, and then recede into darkness, never to return. We will watch, measure, record, and reflect. The wonder will not be in the data alone, but in the awareness that the data represent a rare overlap of time and readiness. The meaning lies in the convergence, in the impossibility of the present becoming real. Perhaps the truest reflection is this: the universe has always been sending messengers, but only now are we able to answer the door. Each interstellar traveler is both fragment and teacher, both relic and revelation. They remind us that timing itself is a force, guiding not only matter but meaning. In their fleeting visits, we glimpse not only the past of the galaxy, but the architecture of our own awareness, suspended within the eternal now of cosmic wonder.